Every time you send a message, stream a video, or load a web page, your data passes through 7 distinct layers of processing. This is the OSI model, the blueprint that explains how networks actually work, from copper cables to the browser in your hands. Layer 1 is the physical layer. The actual cables, radio waves, and fiber optic lines carrying raw electrical signals. Everything here is just ones and zeros pulsing through copper and glass. Layer 2 is the data link layer. It groups those raw bits into structured frames, stamps each one with a MAC address, and hands them to the right device on your local network, the job of Ethernet switches. Layer 3 is the network layer, the global traffic system. It assigns every device a logical IP address and routes packets across routers until they reach their destination network. Layer 4 is the transport layer. This is where TCP guarantees every byte arrives intact and in order, and UDP fires data off as fast as possible without caring, both using port numbers to hit the right application. Layer 5 is the session layer. It opens the conversation, keeps it alive while data flows, and cleanly closes it when the job is done, managing the dialogue between two applications. Layer 6 is the presentation layer, the translator and bouncer. It encrypts data for security, compresses it for speed, and formats it so the receiving application can actually understand it. Layer 7 is the application layer, the part you actually touch. Browsers, email clients, and your terminal all live here, using protocols like HTTP, SSH, and DNS to get work done. The genius of the model is the flow. Sending data means encapsulation. Each layer wraps the previous one as it travels down the stack. Receiving means de-encapsulation. Each layer unwraps the one below as data climbs back up. That's how the 7 layers turn a click in your browser into photons in a fiber and back again. Every packet that crosses the internet follows a layered architecture, and 2 models define how to think about those layers. On the left sits the OSI model, a theoretical 7-layer framework built for teaching and design clarity. On the right sits the TCP/IP model, the 4-layer practical stack that actually runs the global internet. The OSI stack begins at the top with layer 7, the application layer, where user-facing protocols like HTTP and SMTP live. Below it sits layer 6, presentation, handling encryption and data formatting. Layer 5, session, manages the ongoing dialogue between applications. These top 3 layers all concern how software talks to software. Layer 4 is transport, the reliability workhorse, using TCP for guaranteed delivery and UDP for speed. Layer 3 is network, where IP addresses live and routers make forwarding decisions. Layer 2 is data link, managing MAC addresses and Ethernet frames. Layer 1 is physical, the raw voltages, light pulses, and radio waves hitting the wire. Now watch what happens on the TCP/IP side. OSI layers 5, 6, and 7 do not get their own dedicated layers in TCP/IP. Instead, they all collapse into a single application layer, because in real engineering, session management, encryption, and application logic are usually handled by the same software. OSI layer 4 maps cleanly and directly to the TCP/IP transport layer. Same responsibility, same protocols, just a simpler naming. TCP and UDP operate identically in both models, so there is no reason to split them apart. OSI layer 3 maps directly to the TCP/IP internet layer. This is where IP addressing and ICMP diagnostic messages live. Again, one-to-one mapping, same job, different label. At the bottom, OSI layers 1 and 2, physical and data link, merge into the single TCP/IP link layer, sometimes called network access. Ethernet framing, MAC addressing, ARP resolution, and the physical medium itself are all bundled together because in practice, they are tightly coupled and rarely separated. Each TCP/IP layer carries its dominant protocols. The application layer runs HTTP for the web, SSH for remote shells, DNS for name resolution, and TLS for encrypted sessions. Transport runs TCP and UDP. Internet runs IP and ICMP. Link runs Ethernet and ARP. These are the protocols doing the actual work every time you load a web page. So why keep OSI around at all? Because OSI is the cleanest teaching model ever built. A perfect reference for explaining what each function does in isolation. TCP/IP is the leaner, messier real-world implementation, and it wins because it ships traffic every second of every day. OSI explains the theory. TCP/IP moves the bytes. Welcome to this hands-on Linux networking lab. We will use standard Linux utilities to inspect the operating system's network stack, focusing on layer 2, data link, and layer 3 network of the OSI model. Open a terminal and follow along. Every command shown here runs on a real Debian-based system. We begin with clear, which simply wipes the terminal screen and gives us a clean workspace. Clearing the screen is purely cosmetic, but it makes command output easier to read and copy during documentation or troubleshooting. The IP link show command reveals all network interfaces on this system along with their layer 2 MAC addresses. The link/ether field shows the hardware address burned into each NIC, and the state up confirms the interface is active and ready to transmit frames. This is our first direct look at layer 2. Next, IP address show extends the same view to layer 3, displaying the IPv4 and IPv6 addresses assigned to each interface. The init lines show our routable network identity. This is how other machines on the network address us. Notice how low carries the loopback 127.0.0.1/8 while emp0s3 shows our real network address 192.168.1.42/24. The ss tulnp command lists every socket currently listening on the system, TCP and UDP ports bound by active services. The listen state entries tell us which ports are open and waiting for incoming connections, and the process names in the rightmost column identify which daemon owns each socket. This connects our address information to actual layer 4 transport endpoints. Before we touch the network, let's confirm which port a service should use. cat/etc/services head -10 shows the canonical mapping between service names and port numbers. This file is the authoritative reference that tells us SSH is 22, HTTP is 80, and HTTPS is 443. The very numbers we just saw open in the SS output. Now we send a real request with curl, si/http://httpbin.org/get single quote. The I flag fetches only the HTTP headers and S silences curl's progress meter. The response line HTTP/1.1200 OK confirms we reached a remote host on port 80, and the server unicorn/19.9.0 header identifies the application responding. This proves layer 3 routing and layer 4 transport are functional end-to-end. Finally, ARP-N displays the kernel's ERP cache, the table that maps layer 3 IP addresses to layer 2 MAC addresses for hosts on our local subnet. Each entry was learned when we recently exchanged frames with that neighbor. This is the bridge between layer 2 and layer 3 in action. Exactly what happens before any IP packet can be sent on a LAN. Welcome to a hands-on demonstration of the OSI transport layer. We'll explore how Linux exposes layer 4 sockets through practical command line tools, then cross the boundary into layer 7 to see how application protocols ride on top of TCP and UDP. We begin with clear to wipe the screen and give ourselves a clean canvas. This ensures our subsequent output is easy to read without scrollback clutter interfering with the demonstration. Before we look at layer 4, let's glance at layer 2 with IP link show. This lists every network interface on the host, its index, MTU, and operational state. Every TCP or UDP socket ultimately lives on top of one of these links. Now IP address show maps each interface to its L3 addresses, IPv4 and IPv6. Remember, IP belongs to layer 3, but it provides the addressing that TCP and UDP sockets bind to. The transport layer is meaningless without the network layer beneath it. Here is the heart of our demo, says tulnp. The flags mean TCP sockets, UDP sockets, listening, numeric ports, and show the owning process. Each line is a layer 4 endpoint, a port bound to an IP address. And together they reveal every transport layer service the kernel is willing to accept connections on. Each port number you saw in the SS output, 22, 53, 80, 443, is just an integer. The mapping from number to protocol name lives in /etc/services. Displaying the first 10 lines confirms that 22 is SSH, 53 is domain, 80 is HTTP, and 443 is HTTPS. This file is the layer where layer 4 numbers meet layer 7 service names. Now we cross the boundary into layer 7 with curl, si/httpbin.org/get. The I flag fetches only the response headers, which contain protocol version, status code, and header fields, pure application layer metadata. Notice the status line HTTP/1.1200 OK and the server unicorn/19.9.0 header. This exchange traveled over a TCP socket bound to a port number we just inspected. Finally, ARP-N shows the layer 2 neighbor table, mapping the IP addresses we saw in IP address to MAC addresses of our local peers. We've now walked full circle from layer 2 up through layer 3 and layer 4, then jump to layer 7 with curl. The bridge between transport and application is nothing more than a port number in SS, and a name in /etc/services. In this demo we cross the OSI stack using standard Linux tooling. We'll start at the link layer with link and address state, climb into the transport and service layer, fire a real HTTP request at layer 7, and close with an ARP lookup that lives exactly at the L2/L3 seam. Every session starts with clear so the output that follows is easy to read. It wipes the visible scrollback without touching anything on the system. Just a clean canvas before the real work begins. IP link show is pure layer 2. It reports the network interfaces as data link devices, complete with their hardware MAC addresses and operational flags. Look closely at low and ends 33. Each one carries a link/entry, which is the interface's burned in L2 identifier. IP address show adds the L3 layer to the same interfaces. Now you see IPv4 and IPv6 addresses bound to each link. Each address here is a layer 3 identifier riding on top of the MAC we just saw, which is exactly where the L2/L3 boundary lives. tulnp shows the transport layer sockets currently listening on the host, the real endpoints between layer 4 and the applications on top. Each listen line is a process holding a port open, which is precisely how layer 7 services attach to the network. cat/etc/services head -10 maps well-known port numbers to their application protocols. The registry that ties port 80 to HTTP, port 443 to HTTPS, and so on. This file is the dictionary connecting layer 4 ports to the layer 7 protocols that ride on them. Now we go all the way up to layer 7 with curl, OSI, that lowercase, I requests HTTP head only, so we get response headers without the body. The 200 OK and server headers are pure application layer data, riding on top of the TCP socket from earlier. Finally, ARP, and drops us back down to the L2/L3 boundary. Each row maps an IPv4 address, a layer 3 identifier, to the MAC address that actually owns it on the local Ethernet segment. YARP is the protocol that lives precisely on this seam, translating names from one layer to the other in real time.